Welcome to Keentel Engineering, Large Loads and the Grid. This presentation covers three things: the stability impacts of AI data center load, how to model it correctly, and what interconnection requirements actually need to say. Modern data centers are gigawatt scale, inverter dominated, and arriving faster than the grid can expand. That changes everything about how utilities plan, model, and set interconnection requirements. Let's get into it. The scale is the starting point. Single campuses now reach 1 to 2 gigawatts. Some utilities are holding data center interconnection queues larger than their entire existing peak load. On build speed, a campus reaches full load in 18 to 24 months. Transmission expansion takes 8 to 10 years. That mismatch, not the load itself, is the core engineering and planning challenge. The grid isn't broken, it's just being asked to absorb load on a timeline it was never designed for. Three characteristics separate AI data center load from everything utilities plan for: cycling, GPU clusters ramp and pulse during AI training; active power swings that can excite oscillatory modes in ways conventional load never did; opaque, operators honestly cannot predict their future load profile. That uncertainty cascades into every engineering decision downstream. And cascading, a single protection trip at one facility can pull gigawatts simultaneously across a corridor of co-located loads. Not one facility going dark, many at once. Here's the load behavior that most models miss entirely: negative impedance. When voltage drops, a data center's power electronics hold power constant by drawing more current. That's the opposite of how resistive load behaves, and it's the opposite of what planning models assume. In the constant power region, normal voltage range, this negative impedance effect is always active. Every grid-side study must capture it. It cannot be simplified away. In deep voltage sag, behavior switches to constant current. That transition is critical for ride-through and control interaction studies. Simplified models miss it completely. Ignoring negative impedance produces optimistic, misleading study results. Three model types match fidelity to purpose. The average model covers most grid-side studies: constant power behavior, oscillation forcing, conservative ride-through, no harmonics, unreliable at transitions. Right tool for subsynchronous oscillation and load smoothing studies. Average switching adds control dynamics and battery backup unit to PSU interaction. Skips PWM detail. The right middle ground when you need converter behavior without full harmonic fidelity. Use it for control interaction studies. Detailed switching gives you the full harmonic spectrum, and PWM switching. Computationally expensive. Use it for PSU specification validation and high-frequency power quality work. Rarely needed for grid-side studies. More detail costs simulation time without improving the answer. Match the model to the question. 20 milliseconds. Communication and measurement delay. The most underappreciated modeling error in large load integration. Here's why it matters so much. At 0.5 milliseconds, visible oscillation begins. The battery's response is already impaired before it starts. At 5 milliseconds, most damping capability is gone. The battery can barely compensate. At 20 milliseconds, which is a realistic, achievable delay in real systems, the mitigating effect essentially vanishes. Interconnection requirements will be violated. 20 milliseconds is not an exotic failure condition. It's a normal operating parameter that most models don't account for. This one surprises people. Loads can break shafts. A generator's turbine shaft system has resonant modes at specific frequencies. If load cycling hits one of those frequencies and sustains it, mechanical oscillation grows, fatiguing or fracturing the shaft. Even a few megawatts of excitation at the exact torsional frequency is not safe under island conditions. Real load profiles shift phase and vary, making the risk probabilistic rather than certain. But requirements must be set conservatively until that probability can be quantified. Torsional interaction screening is not optional for large load interconnections near generators. 7 things every large load interconnection requirement must address. 1. Load variability limits. 10 to 30 megawatts per minute calibrated to the utility's own generation ramp capability. 2. Voltage ride-through. No industry standard exists yet. Real events have already occurred. Urgent. 3. Power factor. Utilities moving toward unity, shared economic interest on both sides. 4. Harmonics, distortion, and flicker. IEEE 519 exists, but real installations already exceed its limits. 5. Monitoring equipment. PMUS, digital fault recorders, power quality monitors, sub-second granularity required. 6. Load models for studies. Specify model type, quality, and submission requirements at application. 7. Outage and recovery coordination. Gigawatt load outages are uncharted territory. Existing protocols were written for generation, not demand. 2 approaches to setting load variability requirements, both in active use. Surgical frequency domain analysis identifies specific torsional frequencies and sets tight limits, a few megawatts only at those frequencies. Precise, but requires more study data to execute correctly. Blunt, a simple megawatts per minute cap on total active power variation. Figures like 10, 20, or 30 megawatts per minute appear across current utility requirements. Conservative by design, written with limited data, and will need tuning over time. Neither is wrong. Requirements written today are conservative first drafts. They will need continuous tuning as real-world operational data accumulates. The grid was built for predictable loads. Data centers are not predictable loads. The engineering response covers 4 areas: load modeling and average, switching, and EMT fidelity levels, torsional interaction, and subsynchronous oscillation studies, site-specific ride-through and performance requirement design, and interconnection process framework development. The tools exist, the methods are established. What's needed now is consistent application across utilities and developers. Reach out to Keentel Engineering at keentelengineering.com.